Hi, there's been a request to solve a related rates problem, so that's what I'm going to do. I'm going to take the snowball problem from our Chapter 4 test and first semester final and talk through it as I work on it. Thank you for being patient. It's going to be awkward as I fumble through this thing. So the first thing we need to do is we need to state what we have and what we need. So, what we know is dA dt is going to be -1 inch squared per minute. And what we want is dV dt. And that's the thing we don't know, obviously. So, the goal for this problem is to relate these two rates. And most students that have trouble with this, they try to go right to an equation that has dA dt in it and dV dt in it. The problem is you can't jump to that part at the end, and so related rates is not necessarily descriptive of the first step in the process. Related rates tells you what you're going to do. You're going to relate two rates, but you have some work to do before you can do that, which means we're going to write some equations and mess with them that don't have rates in them. We're going to save the calculus for the last step, well, almost the last step in the process. So, let's move these aside. This is going to give us the idea of what we want and what we have. And let's write a couple equations. They're actually the ones that are written up here. Area is 4 pi r squared. So area is 4 pi r squared. And volume is 4/3 pi r cubed. And here's my goal. I want to take this thing, this area equals 4 pi r squared, and rewrite it so that I can take it and smash it into here. That's my goal. So the first thing I need to do is manipulate a equals 4 pi r squared so I can put it in for r in the other equation. Now before I do that, an important question. Why would I put that top relationship in the bottom equation? Why not the other way around? And the answer is you could. Because all you really need is an equation that has a's and v's and no other variables. So, let's do it. I'm going to put u up there. And I'm going to say then that, well, from that relationship, a divided by 4 pi should be r squared. So then the square root of a over 4 pi should be equal to r. Well, now I can take that and I can smash that into that second equation, and I come up with this. Volume is equal to 4/3 pi, and then instead of r, I'm going to replace it with its equivalent relationship, which is the square root of, and I wrote 4 over here. You caught my error. I didn't catch it. The square root of a over 4 pi. Bam. To the third power. So, I have now the relationship that I want. It's an equation that has only volume and area for its variables. Right now, I could do calculus, and then in the process of doing implicit differentiation, and that's the quote-unquote do calculus I'm talking about, in the process of implicit differentiation, dV dt would show up, and dA dt would show up, as long as I differentiated with respect to time. But see, in this current form, it's going to be ugly, and I'm going to have a lot of algebra to battle. So, it's advantageous to spend a little time cleaning this relationship up so the calculus is a bit easier to manage. So that's what I'm going to do. Alright, so I move that over, give myself a little bit of room here. What I want is I want to rewrite this thing with some fractional exponents. So volume is 4/3 pi times a over 4 pi to the 3/2. I don't know if there's anything else I can do right now. I think I need to go do some calculus. So I guess you'd say that isn't much cleaning. Is there more that I can do? No, I don't think so. Okay. Well, there's the house cleaning that I did. Not much, but it'll help. And we're going to do calculus on that relationship right there. So let's do it. Let's differentiate with respect to time. So dV dt equals, now 4/3 pi, this is just crazy old man, it's a constant, comes along for the ride. So I'm going to write it as 4 pi over 3. you could leave it as 4/3 pi, times the derivative, so 3/2 of a over 4 pi. Now this is a little chain rule, so I got to subtract 1 from the 3/2, and it's going to make it 1/2. And then the chain rule factor is going to be the derivative of the inner, which is that a over 4 pi. Well, there's a constant in there as well, so the derivative of a over 4 pi with respect to time is 1 over 4 pi times the derivative of a with respect to time. So here I have it. I have the relationship. I have dv dt and dA dt in an equation. I have successfully related these two rates to one another. Okay, so now I'm going to do a bit more cleanup. Let's see, we'll move you over here. Sorry, I'm not doing a very good job of working vertically here. Okay, so it's just some fraction math here. Let's do some cleanup. I've got a 4 pi here and a 4 pi here, so those are going to cancel. I got a 3 here and a 3 here, those are going to cancel. I think that's it. So dv dt then, I'll write it over here, dv dt is going to be 1/2 times a over 4 pi to the 1/2 times dA dt. Now, up in the original problem, it said it wants to know the rate of change of volume with respect to time when the radius is 3 inches. You'll notice in our equation, we don't have any more references to radius. So, here's the side work we're going to have to do. We're going to have to revisit the original volume equation, that's this guy up here, and ask him a question. Oh, something like this. Hello, Mr. Volume. What are you when your radius is 3 inches? So I'm going to plug 3 inches into that equation, and it's going to spit out a volume. Now, how does that help me? I don't know if that does help me. Does that help me? So I'll get a volume. Oh, see, here's the problem with that. There's nowhere to put that in this equation. See, the only reference to v in my new equation is in dv dt. I have a dA dt over here as well, but I can't put a volume in there, obviously. See, I have a place to put in a value, but it's not for volume, it's for area. It's right there. Right there. I'm going to put an area value in to replace A. Here's why that works. That works because at this instant in time, there is an area, surface area in particular, when the radius is 3 inches. And by taking that value, which we're going to find in just a second, and plugging it in here for A, then the resulting dv dt value will also be, it will also correspond to that instant in time. Alright, so let's do this. Alright, so I gotta clean up my workspace here a little bit. Let me do some erasing, if it's gonna let me do some erasing. I don't know if it is. I don't think it likes me. Oh no, I don't want to delete that. Let's do some erasing. Hello? No erasing. Alright, well, let's do some rearranging then. Let's take this guy and move him here. Alright. So here's what I need to do. I need to go back to this equation here, a equals 4 pi r squared. And I need to plug in 3 and see what area I get out of there. So a equals 4 times pi times 3 squared. So I'm going to get, what, 36 pi? And 9 times 4, yep, 36 pi. Now I can take that value, 36 pi, and I can do what I said I was going to do, which is take it and put it, nice curvy arrow, right there. So, let's do that. Alright, let's take that curvy arrow. Oh, no good. Well, 36 pi, we remember that. Thank you for your patience as I learn this stinking program. Alright, so we're going to take 36 pi and we're going to put it into this equation right here. So, dv dt is equal to 1/2 of 36 pi over 4 pi to the 1/2 times dA dt. Okay, well, we can do some cleanup now. I think that's pretty obvious, so let's do some cleanup. It's getting so small, I hope you can still see that. All right, 36 divided by 4 is 9. The square root of 9 is 3, and the pi's are going to go away. So pi's are gone. Pi's are gone. 36 divided by 4 is 9. Square root of 9 is 3. Yep. Sorry, brain fart there. So I think this whole thing's going to simplify to dv dt is equal to 3 over 2 times dA dt. Now let's revisit this initial part of the problem. What we're trying to do is we're trying to say, what is dv dt when the radius is 3 inches? Well, we figured out the area at 3 inches, so we've locked this thing down at the right instant in time, but we still don't have a numeric value. I don't want an answer that says dv dt equals a number times another rate. I want dv dt equals a number. So, this is where we use what we knew at the beginning of the problem. We knew that at that instant in time, the rate of change of area with respect to time is -1. So -1 goes in there. So what we have then is dv dt is equal to -1 times 3/2. So let's write it here, -3/2, and let's put units on it. I think it's going to be inches cubed per minute. Inches cubed, that's supposed to be a 3 per minute. And there it is, the answer to the dreaded snowball problem. Thanks again for your patience with this software, and I hope it helped.